Hello, and welcome back to Physics 41, University Physics 3. So far, we have discussed electrostatics, which deals with charges at rest. And in the previous chapters, you have started discussing about electrodynamics or moving charges, which essentially creates what we call current. Now, we are still on the part of we are actually on the heart of electrodynamics, which deals with the consequence of moving charges or current. And that consequence is a phenomenon called magnetism. So in this chapter and in the next chapter, we will try to explain how electricity or how current is related to magnetism. So this chapter will focus on magnetic field and magnetic forces. We will actually just be introducing the concept of magnetic field and how it acts forces on other, say, charges or other systems. So for the first lesson of this chapter, we will be talking about the basics of magnetism. So magnets and magnetic materials. So magnets always exist in pairs. So the magnets that we know, the refrigerator magnets that you have, are what we call permanent magnets, and they always exist in pairs. So it's actually a pair of a north magnetic pole, or what we call an N pole. So N stands for north, and a south magnetic pole. So S stands for south. So take note, these are different from the north and south poles that you have maybe familiar with. So these are magnetic poles. So even if you have a magnet and you try to break the magnet exactly at the center, you will still get two dipoles. You will always get a pair of magnetic poles, a pair of N and S poles. So everything in electricity and magnetism are symmetric, except for this property of magnets, wherein you cannot find a single north pole or a single south pole, unlike in electricity, where you can find a single positive charge and a single negative charge. You can also have a pair of positive and negative charges. That's what you call an electric dipole. In the case of magnetism, it's always a magnetic dipole. It's always a pair of of a north and a south magnetic pole. So magnetism is essentially the action by magnets wherein they can attract other say magnets and other metals for that matter. That's actually the phenomenon called magnetism. So similar to electricity or electric charges, where like charges, they will repel. A positive and a positive charge and a negative and a negative charge will repel each other, will try to push each other away. And opposite charges, a positive and a negative charge, will try to pull each other towards each other, hence the attraction. A similar thing happens in magnets. So magnets of opposite poles attract. So a north will attract a south and vice versa. And like poles will repel. So as I've said earlier, electricity and magnetism are virtually symmetric to each other. Whatever is whatever property there is in electricity, there's also a counterpart in magnetism. Just except for the a single pole or a monopole. There's no monopole. There's no single N pole. There's no single south pole in magnetism. So like poles will repel, a north will push another north pole away. The same thing with the south, two south poles. So when metals are exposed to a magnet, they actually become temporary magnets. So we will actually discuss the different types of magnets in the next, or magnetic materials in the next slides. So they become temporary magnets. And actually, if they have been exposed to a magnet for a very, very long time, that's the time that they become a permanent magnet. So it doesn't matter if it's the North Pole or the South Pole, a metal or a conductor will always be attracted to the magnet, to the poles, or to any poles of a magnet. It doesn't matter if it's a North Pole or a South Pole. So if you will notice, in this case, you will notice that this nail or this metal is actually not directly in contact with a magnet, but it's still attracted because some of these nails or metals here become temporary magnets. So the short version is metals actually find magnets very, very attractive. So it's very attractive to them. Magnets are very attractive to metals. So let's now discuss the three different types of magnetic materials. In any material, there's what we call magnetic dipole moments. They are basically tiny magnets in everything. So since they're a magnet, one side is a north pole and the other side is a south pole. And the direction of these magnetic moments is like this. So the head is the north pole, the arrowhead is the north pole, and the tail is the south pole. We will just expound about magnetic dipole moments in the succeeding lessons and in the next chapter. So in a normal material, when there is no magnetism, or there's no magnets around, or where there's no external magnetic field, so I will just expound about magnetic fields later, but it's just the same with electric fields. So since there's still no magnets around, there's no magnetic field, then the magnetic moments in a normal material are aligned randomly. So they have random alignment, and which makes this ordinary material to have no magnetism. Now, if you expose this material to an external magnetic field, such as placing it near a magnet, there are three different reactions depending on the type of material. So if your material is ferromagnetic, such as materials containing iron, nickel, or neodymium, all or most of their magnetic dipole moments, the tiny magnets inside them, become aligned. They align with the direction of the magnetic field. And this causes them to have a very strong magnetism. So ferromagnetic materials are actually the best candidates for making permanent magnets. So the magnets that you see every day are mainly composed of iron, nickel, and neodymium. So usually right now, the commercially available, the strongest commercially available magnets are made of, permanent magnets for that matter, are made of neodymium. So those are the materials for making permanent magnets. Now, there are also other types of materials where instead of aligning with the magnetic field, they actually misalign or disalign with the magnetic field in such a way that if they disalign, then this is now the south pole and this is now the north pole of the material, essentially having a repulsive or repulsion effect. And these are the properties of superconductors. So if you place a superconductor such as this one on top of a magnet, this is a magnet here, it will actually get repelled. It will not be attracted to the magnet, but instead it will get repelled. And of course, superconductors have other properties, just like this one. It actually locks itself with the field. So we will not discuss that in this course. So the third class of magnetic materials are what we call paramagnetic materials. So in paramagnetic materials, only some, not all, but only some of the magnetic dipole moments, the tiny magnets and everything, align with the electric field. So this is the case for aluminum. So again, not all metals are ferromagnetic, only iron, nickel, and some other materials. Aluminum, which is another metal, is paramagnetic. It has very weak magnetism. Our human body is a paramagnetic material, and basically everything else are paramagnetic materials. So every material in the world can be categorized into these three: ferromagnetic, diamagnetic, paramagnetic. So in the case of the human body, we have tiny magnets in our body, and we call this the magnetic dipole moments. And this is actually taken advantage by the MRI, magnetic resonance imaging. So if you have an MRI scanner, if you have experienced MRI scanning before, you can actually scan your body by exposing your body to a magnetic field, such as, I think you have seen this in movies. There's a circular chamber. You remove all of the metals in your body. No, this is just a joke. There's no woman inside the MRI chamber. So every cell or every tissue in your body has different amounts of magnetic dipole moments. And because of this variation, you can actually scan and differentiate a healthy tissue as compared to a tissue with cancer, for instance. So that's the main purpose of MRI. It's for medical imaging to determine cancer cells and other say defects. So the Earth is actually a giant magnet. So this is the Earth. It's actually a giant magnet. So, but it is the situation is reversed. The North Geographic Pole, the North Pole that we usually, in layman's term, the home of Santa Claus, is actually close to a South Magnetic Pole. And the South Geographic Pole, Antarctica, for that matter, is actually close to a North Geographic Pole. And these blue lines that you see here, which points from the north, from the north to the south, outside of the Earth, are called magnetic field lines. So they point from the north to the south, and inside they point from south to north. So they actually form continuous loops. And this whole configuration here of lines is what we call a magnetic field, the magnetic field. So the Earth actually has two types of fields. It has a gravitational field, which is directly towards the center of the Earth, and it has a magnetic field which loops around the Earth. So when you place, so the pattern, the magnetic field line pattern of the Earth is just very similar to the magnetic field line pattern of a bar magnet. So you will see here that magnetic field lines come out of the North Pole, goes to the South Pole, and then from south to north inside. So it forms continuous loops. Now, when you place a compass needle is actually a magnet. So when you place a compass near a magnet, it just basically aligns itself with the magnetic field line. So if you put a compass here, it will align with the direction of the magnetic field at that point. If you put a compass there, it will just align with the magnetic field at that point. So similar, if you put a compass say near the Earth, it will just align its magnetic field near the or magnetic field at that point. So in this case, the direction of the magnetic field is upward. But if you place a compass in that direction, the direction of the magnetic field is now it's curving. So that's now the direction of the magnetic field. And again, if you place the magnetic field there, that is the direction of the compass needle. So for the compass needle, the red part is actually the North Pole. The white part, or sometimes it's blue, is actually the South Pole. So the North Pole, the red part of the compass, will actually points to the south magnetic pole of the Earth. So the North Pole in your compass, the N, the one with the N, the red, usually it's colored red, it actually points to the south magnetic pole of the Earth, which just so happens, that the south magnetic pole is close to the north geographic pole of the Earth. Essentially, you're just essentially saying you're pointing to the north geographic pole, but actually you are pointing to the south magnetic pole of the Earth. So how do you visualize magnetic field lines? So I guess you have performed this experiment when you were in high school. So you use iron filings. So you use iron filings, you spread it near your magnet, you tap the table or the paper with the iron filings so that the iron filings will align themselves with the magnetic field so that you can visualize the magnetic field lines of a magnet. So the magnetic field are not visible to our eyes, they're imaginary. They're just similar to the electric field and the gravitational field. They're imaginary or invisible. But in the case of magnetism or magnetic field, we can actually visualize them using iron filings or using a compass. You can visualize them using a compass. So you use your compass, scan it around the area, map the direction so that you can map the direction of the magnetic field in that area. So these are just some examples of magnetic field line patterns for repulsion. This is for repulsion and this is for attraction. Again, you can visualize these two if you use two magnets and you put iron filings between them. Okay. So let's now go to the main question for this lesson. What is the relationship between magnetism and electricity? So this relationship was introduced by the experiment done by a physicist called Hans Christian Ørsted. So his experiment is very simple. He has a compass, and then he puts the compass on top of a wire, a conducting wire. So initially, he aligned the direction of the compass to the length of the wire, and initially there's still no current. Now, what's amazing is when he now passes a current through the conducting wire, the compass needle is actually deflected northeast in this matter. And what's more amazing is that when he reversed the direction of the current, the deflection of the needle also reversed. It's now in the northwest direction. Now, if you will notice from the property of magnets, only magnets exert force on other magnets. So the reason why we experience magnetism, because there are magnets inside of us. Now, in this case, we know that only magnets or its field, called the magnetic field, can change the direction of a compass needle, right? Such as the magnetic field of the Earth. So this can only mean that since there is a change in the direction, therefore current or moving charges must also be magnetic. So, a conclusion made by Hans Christian Ørsted uh, states that magnetic field can also be created by moving charges or by current, in addition to the electric field. And a magnetic field essentially exerts a force on other magnets, such as moving charges or current carrying conductors. So, for the next topic, we will be discussing about how the magnetic field exert forces on moving charges and current carrying wires or current carrying conductors. So that's it for this uh, lesson, and I hope you have learned something. So I will see you again in the next lesson. Bye bye.